Good morning and welcome to this presentation, which deals with the compromise between the use, the historical value and the seismic safety of historical buildings. There are some different contrasting needs in terms of safety and use and preservation of the historical value of this type of buildings. And I will present you one specific case studies which is related to the palace and bell tower of Cingoli municipality in Italy. Let me first introduce you the Cingoli municipality, which is a municipality of the Marche region in central Italy. It has around 10,000 inhabitants and the 150 square kilometer area, so it's quite large with respect to the population. And the altitude of Cingoli is around 800 meters above sea level. This gave the name of balcony of the Marche region, because from Cingoli you can see all the land until the Adriatic Sea and the sea itself. Here you can locate the municipality on, let's say, on Italy, and knowing that the Apennines are in the central part of Italy, aligned with the Italian territory, you may understand that the municipality is between the Apennines and the sea. Since the Apennines is the most risky seismic hazard, most risky seismic zone in the central Italy, Cingoli municipality is in an intermediate seismicity area because it has already a certain distance from the mountains. But still there is some seismic risk, so that it is included in seismic zone number 2, which is intermediate. The most risky zone is 1, and the less risk is 3, and 4 is negligible, I would say, presence of earthquakes. This is the palace and the bell tower as they are now. The building is under the protection of the Ministry of Cultural Heritage, and it is used as a museum in the underground and ground floor, and as town hall at the upper story. This means that according to Eurocode 8, but also according to the Italian code, the important class is 3 for the use of museum, and it is 4 for the town hall use because of the importance of some offices during emergency. The building has been damaged by the 2016 Central Italy earthquake with a magnitude 6.5, and it is at the distance of about 60 kilometers from the epicenter, so we cannot really say that it is in the epicentral area. Nevertheless, the building, we will see, suffered some damage, and due to this it has been included in the reconstruction plan, and some governmental funds have been allocated for the seismic retrofitting of the palace and the towers. So at this point the municipality has several options in terms of type of intervention, and they decided to perform some specific studies in order to decide about optimal allocation of resources in terms exactly of different type of intervention, different type of use also of the buildings that can be done. To this end, there were basically 2 main questions raised by municipality. The first one is, what is the safety level that can be achieved with reasonable cost with not intrusive intervention, meaning with intervention that are appropriate to buildings under the protection of Ministry of Cultural Heritage. And the second question is this safety level compatible with the use of the building, with this important class 3 and 4, based on the presence of the museum and of the town hall in the buildings. You have to know that in Italy, but I think in as many other countries, when buildings are under the protection of the Ministry of Cultural Assets, there is no obligation to achieve a specified seismic safety level. This is obviously because there is the need of preserving the monument, preserving the historic and architectonical issue of this building. But nevertheless, for the administration, it's not straightforward the use of that building if the safety level does not reach some minimum level. So there is no specified minimum level, but nevertheless, from a social point of view, there is some concern if you use a building as a town hall and you know that it has a very poor resistance. So it's a quite clever approach and smart approach from municipality, from the administration point of view. It's not common to find municipality that decide to perform such studies before deciding about the use and the intervention of the building. So the first question about which is the safety level that can be achieved in this building, it's a question that is addressed to the engineer. The engineer will answer after some specific assessment study. While the second question is that safety level compatible with the use of the building? Since there is no code prescription, then at that point it becomes a social political issues, and it's the mayor, the council, that has to decide about this, but based on the information provided by the seismic engineer. So let's start now presenting the activities that has been done, starting with the knowledge phase, which you know is the initial phase of any assessment on existing building. The second step is to build the model and then to run the analysis in the actual configuration, and then including intervention, check the final resistance of the building, evaluated the cost and sustainability of the interventions. So the knowledge phase. The knowledge phase includes in these case studies the analysis of the protections under the Ministry of Cultural Heritage, the history of the building, the geometry of the building, the intervention that have been done in the past, description of the building components, and then the survey campaign that has been done to complement all the available information. Protection of the Ministry of Cultural Heritage is in terms of two decrees. The first one is related to the historical architectural value of the building, and it has been issued in 1913. And the second one is related to the landscape, and it has been issued more recently. In any case, it's not possible to perform any intervention on this building since 1913 without prior approval of the competent offices of the Ministry of Cultural Heritage, which in this case are the regional offices. History of the building. The building was built in the 13th century for what concerned the town hall and the central part of the palace. Even in 15th centuries there are information about structural works related to repair of some element. For sure in the 16th century the facade was added, but also the stairs on the back because of the use of the theater we will see later of the building. There is a clear inscription in Latin language in the facade that says that the facade has been built in 1531. The scheme of addition is such that the tower, the bell tower, and the initial part of the building were built in the, as I said, in the 13th century, and then the stairs were added, the facade was added, and then the final scheme. In the second half of the 17th century, it was intermittently used as a theater at the second story. But from 18th century, the use of the theater was more, let's say, continuous, and there was a theatrical congregation that committed some works for the decoration and paintings of the second floor devoted to theater, and the theater itself was devoted, quite interesting, to Verdi after he stayed in 1813. So this is a view of the theater as it was. It had three tiers of boxes, and the stalls at the beginning were equipped with benches and then later with numbered seats. Basically, it has the typical story of all theaters. And this is the view of the buildings as it was in the early 1900 and few years later. After the First World War, the use of the building was, the building was less and less used, and poor maintenance brought to declaration of unfit to use, and it was closed. So it wasn't anymore used as a theater, anymore used the wood building. In the 70s, and we don't know if and which works were done in order to allow it. The lower part of the building was in the lower part was arranged a museum, and then it was open to the public. After that, from the 70s, a lot of many refurbishing works started on the buildings until basically nowadays, until the 2000. These are pictures of the buildings in the 80s, and from where you can see the poor maintenance of the external walls and poor maintenance of the mortars as well. It can be seen from this picture. And this is as it is now. And the underground stories, the museum, and the coat of arm hall in the second story, which is a very nice hall of the municipality, where you can see also several paintings that have been moved here temporarily because of the 2016 earthquake that damaged the churches where these paintings were located, and then municipality brought them in this hall. So geometry of the building. Geometry of the building, you can initially see a 3D view of the building that comes from the model, but gives you an idea of how it is the buildings with the different part added along the centuries, and it's quite complex, parts with different heights, with different setbacks, quite complicated to understand all the relationships. The underground floor is just located on one part of the building, only in this part. The ground floor, you can see the thickness of the wall on the ground floor, really significant. We will see later they go up to 2 meters, more than 2 meters in thickness, and this is the bell tower. This is also the facade of the buildings, which the first floor rests on columns, and we've seen from pictures before. The first floor basically follows the scheme of the ground floor, but you can see, for example, that here there is not anymore the structural wall. These are the internal stairs, and this is the block with the stairs for access to the theater in the previous time. And at the second floor now we have the coat of arm hall, which is the hall that we've seen in picture before, but there is also this huge council hall, which comes from the previous theater hall and now is used as council hall. Two sections, longitudinal and transversal. We can see the bell tower, the council hall, which is this as well. The roof of the council hall is made of trusses, wooden trusses, and you can see here in the other section. And this is the block of the stairs on the back here. Recent intervention. This part is quite complex because there have been many interventions in the past. So to understand how it is now, it has been needed very detailed study of all the documentation that the municipality had, and in this again I want to let you know that all information was at the technical offices of the municipality. This is not always the case, even for works dating back basically the 80s. So the initial design started of the refurbishing of this building started in the 70s. From I mean, ideas of the municipality. Then an architect supported the municipality with a more comprehensive design in the 80s that was implemented in two phases, but the second phase design was never implemented. Then there was the entrance hall refurbishment, and then in the end of the 80s comes an engineer which basically implemented with different solution what was initially conceived by the second phase design of the architect Bernardi, and it was implemented. This design was implemented in two phases. After that, there was the refurbishment of the facade, and after the 1997 Umbria Marche earthquake that damaged the palace, there was a seismic upgrade design, and the works were implemented over the years 2000, 2001. So quite complicated. We will go briefly to all these phases. The initial design, let's understand a little bit, because this gives the guidance for all the other designs. It was not implemented exactly in this way, but we will see a lot of let's say similarities in the subsequent design. So what they planned at that time, to substitute the floors with reinforced concrete floors at the first floor and the second floor. Then to add an intermediate floor with new columns and starting from the walls, and a new floor in the theater hall that was quite high. So they wanted to use that space. And basically then to a little bit change and in order to upgrade the structure of the wooden structure of the roof, so intervention on the roof and retrofitting of two edge columns of the facade. So basically these were the ideas of that period. The municipality prepared the design, the first phase design, which contained only the reinforced concrete, the new reinforced concrete floors, but the tender procedure was unsuccessful. So basically there were not enough money for this, I would say, for all this activity. Then as I told you, this architect Berardi arrived, supporting the municipality for a comprehensive design, which is very similar, nevertheless, to the municipality design of the 70s. This design was approved by the municipality, but we will see will never be approved by the superintendents for cultural heritage of the Marche region. For this design, we have the architectonical drawings and we have the structural drawings. So for the structural drawings, we have the new floor, the reinforced concrete new floors. We see that there are several beams resting on tie beams. These are tie beams because they are placed on the wall, while these are classical beams, and the slab between the beams, reinforced concrete slab with clay, swallow clay blocks. This design was implemented in two phases. In the initial phase, they substituted the floors in just one part of the building, first and second floor of that part of the building. The drawings that I showed you before, it's related to the second floor, while for the first floor, the intervention will be even in the future just on these parts, on half of the floor. The first part we will see later will be implemented with different solutions. The design for the whole floor we have for the second floor. For the first floor we just have sketches, and from these sketches we understand that there is a ring beam, reinforced concrete ring beam, and pre-stressed prefabricated reinforced concrete joints with some details about the reinforcement. As I told you, superintendents was not informed about this project, so when they presented this design this design to the superintendent, they issued negative opinion because of this new third floor, which was supposed to be realized in the theater area. And they suggested not to realize this additional floor, rather to use this huge hall for other public events. So somehow the project was, the design was a little bit rearranged, and we went through, we arrived to the second phase design and second phase implementation of the works. That is really very well detailed in the work record book. So in this, for this second stage, second phase design, which does not include the third floor, we have the completion of the second floor reinforced concrete floor according to the design. So basically with the beams, the reinforced concrete type beams on the perimeter, the beams and the slab, exactly as in the drawings. While for the part of the first floor, which was not substituted during the first phase work, it has been decided at the time to make a new floor with steel beams and clay blocks. At that level, there are the existing vaults. In bricks vaults, very nice. So they kept these vaults, and on top of them, but separated from them, in order to have two different systems, they built these steel beams. So at this moment, what we have: steel vaults and steel beams in a steel floor in this part, reinforced concrete floor in this part, reinforced concrete floor for the whole second story. And this is very well detailed in the record, in the work record book. With the same during the same second phase works, they also decided to demolish these internal bearing walls that I mentioned before, and the added part, the red part added, are very limited to the demolished part. So basically, this resulted in the increase of the building vulnerability. At that time, it was quite common to remove a part of bearing walls and to consider only the vertical loads on this type of, let's say, the implication of this removal for the vertical loads was considered, but not usually for the seismic loads. Also, I wanted to tell that at that time it was very common to implement works in different phases, and we will see it will be also in the other future works on this building. Nowadays, it's not anymore the case, because you intervene just on a part of the building. You cannot use the wood buildings when you have to work also on plants or systems. It's really difficult to have just half of the buildings with electrical wires or with plumbing system. It's nowadays it's not done anymore. But in the past, they had limited amount of money, and they did the works step by step. Another interesting intervention that has been done at that time, and we discovered it on the work record book, otherwise it would be very difficult to detect, is that they wanted to hide some systems on the facade. So they built a separate wall, very thin, 5 centimeter wall, separated 5 centimeters from the existing masonry wall, in order to hide these plans. And this has two implications. First, if you don't know, you think that the wall is 10 centimeters thicker than in reality, so you overestimate the resistance. And second, this very thin wall, 5 centimeters, it's anchored only at the top, maybe at the bottom of the floors. So it has some seismic vulnerability for sure. It may cracks and overturn very easily. And it's not connected. It's not connected to the existing wall. It's completely separated. The roof, what has been done at that time in the roof, from pictures, because it's not mentioned in the work record book, but from pictures of that period, more or less, we know that there are already some steel plates at the end of the trusses. and we know that there are some iron ties that connect these plates at the end. So basically, the roof connect the two vertical walls of the theater, and this seems to have been done on that period. They also retrofitted with micropiles and epoxy injections the two corner columns of the facade. There is no specified for which reason they've done this intervention, and it's not included in the design, but it's a direct labor commitment from the work supervisor and municipality during the works. So there is just this type of specification, no more than this. And when we will address the soil features, then we may understand or one of the possible reasons why they decided to implement such piles. Architect Berardi presented a second phase design. So after having, let's say, substituted the floors of first and second floor, he presented a new design to the superintendents, to the municipality, in which there is still an added floor in the theater area, this time built with steel elements, steel columns and steel beams. The steel columns start from the existing walls, and there is also another steel floor that makes the cover that covers this new added floor. So basically there are two added stories, one to be used and the other one just as the roof of the new one. This design was approved by the Superintendency of Marche region, quite surprisingly, because the previous design with the same added floor, even if in reinforced concrete and not in steel, was not approved, but it was never, probably hopefully never implemented. Next works on the buildings was the refurbishment of the entrance and of the facade, the lower part of the facade. There were mainly no structural works. The only structural works or related to structural works were the filling of the bed joints of the vaults at ground floor and the repairing of these vaults. So basically in all this area the vaults were somehow repaired and maintained. In the 80s, in the last 80s, arrived engineer Morosetti, who replaced architect Berardi, supporting the municipality, and he prepared a new design again in phases, which was mainly devoted to the refurbishment of the second story. So the floor of the second story has been substituted, but all the walls and the other part of the theater were not usable, not yet usable. So in his design is proposed to strengthen the masonry walls at the second story, so the masonry of the theater, and this has been done in practice through the remove and replace intervention, while in the design it was considered mortar injections, and we will see the implication for this. He demolished the stairs in the block of the stairs in the back part of the buildings and added new floors, steel floors there, and then two other minor intervention, an internal stair in steel and a small mezzanine at the second floor. The work started in 1990 and lasted three years. This is the picture, a view of how it was before these refurbishment works and strengthening works of the theater. You can see it was not possible to use it, obviously. And this is the strengthening of the masonry walls of the theater area. That again comes from a very detailed world record book that municipality has kept in their archives. So basically what happens in the design, I told you, was considered the injections of all the walls, meaning that every part of the wall, even this part, should have been retrofitted according to design, while in practice they intervene only on this yellow part with this let's say substitution of the existing masonry and replacing with new elements. So it was an here and there intervention and not a comprehensive intervention on all the walls. As for the block on the back, as I told you, the stairs were demolished. They were in this position, and new steel floors were added with tie beams around the block, and steel beams transversal, and corrugated sheet floors with reinforced concrete slab. So not heavy floors, and well connected to the wall. Even in the wall, the existing wall of the stairs, there were implemented some remove and replace intervention in the yellow part highlighted in these pictures. This is the mezzanine, which I mean, it's a relatively small added part at the second story in the theater area. On the back, it was built, this mezzanine, for allowing having some machines, technical, let's say, area for technical, tools, and again in steel elements with corrugated sheets and more reinforced concrete slab. So it's quite light, and it's not connected to the building. It's not really significant. As for the calculation of the intervention made by the engineer declares that it's full retrofit with a shear factors of 34%, meaning that the capacity of the building is 34% of the weight. This is quite huge value. So I went through calculation and I found some inconsistency. First of all, the same shear resistance is adopted in both directions, in the longitudinal and transversal direction of walls, while usually we consider only in the longitudinal direction. In the transversal direction is assumed as not resistant. So this can be seen from the output of the calculation. In the x and y direction, the resistance is the same. As a second let's say I found that the resistance of the wall that has been considered in the calculation is quite high. For unstrengthened material, it's 0.9 decanewton per square centimeter, which is about 9 tons per square meter. So it's a quite high value, typical of very well square stone masonry with thin joints, and it's not really a proper value for irregular masonry with not resistance or degraded mortar. In the calculation, it was considered double side jacketing, reinforced jacketing of each wall, so quite different from the remove and replace intervention. And the resistance adopted, it's quite acceptable for that type of intervention. Not all the wall in the buildings had some type of intervention. So it's due to all these reasons. The results of this 34% of shear capacity and full retrofit, in my opinion, it's especially even because the reinforced concrete jacketing has not been implemented at all, so it's quite questionable. So full retrofitting of this building is quite questionable. After that, there was the refurbishment of the facade. In that refurbishment in the mid-90s, basically there was a substitution of the main elements of the wooden roof of the highlighted part in the picture, so over the facade and over the coat of armor room, hall and stairs, internal stairs, and also some intervention on the what we call camorcanna walls, on the walls that are made with bamboo and some mortar that are quite rigid and brittle, I would say. Also elements, they can crack immediately, and since they are fresco and the interior part, they were strengthened with some additional elements and some resins. There are no calculation, or there are some simple calculations for the roof element. New added the roof element. These rough calculations are, I mean, proper, consistent. So the size of this element is appropriate. And we arrived to the 1997 Umbria Marche earthquake, which was the earthquake that Cingoli municipality suffered before the 2016 earthquake. It was at that time an earthquake with a lower magnitude, 6 instead of 6.5, and the distance from epicenter was 50 kilometers, so a little bit less than the 60 kilometers of the 2016 earthquake, nevertheless not in epicentral area. At that time the damages were mainly in the separation of the heavy decoration of the facade from the brick wall of the facade of the 1500, some important vertical cracks that were, let's say, that demonstrate the initial overturning of several walls, the cracks in the Camorcanna walls with some damages on the stucco, and quite important vertical cracks in the bell tower, in the belfry tower. According to this, the palace was inserted in the reconstruction plan, got some governmental fund. At that time, it was very common to have some upgraded design with calculation only on the elements where you intervene, not with the global assessment. So we found in this design basically this type of works, repointing of the mortars bed, and this repointing is basically removing the mortar from the outside part of the bed joints and replacing with new one. But it can be done just for several centimeters, and when you consider that the walls are maybe 2 meter walls or 1.5 meter walls, you understand that this intervention, it's in percentage of the thickness quite limited. Remove and replace intervention on several masonry walls, especially where there were holes found or lack of connections. Strengthening of the edge column again of the facade, strengthening again of the Camorcanna walls, and some new floors in the towers, wooden floors, but really this is less important. So let's see, for example, how the anchoring of the decorating elements to the facades was done through steel bars perforated through the decoration and anchoring to the wall. This is quite interesting and effective intervention. While for the remove and replace intervention, you can see here some example. First of all, you have to notice that they have been implemented mainly with brick elements, while the wall is natural stone masonry wall. And in addition to this, it seems that there is no significant connection between the new elements and the old elements. So this type of intervention may be in some case questionable. And here are pictures of the retrofitting of the edge columns. It is reported in the calculations the calculation report that they have found some brick elements inside of these columns instead of full stones. Instead of stone, so they decided to replace with stone. And we arrived at this point to the 2016 Central Italy earthquake. I forgot to mention that in the previous intervention, a lot of iron ties were also implemented. We will see also later. I think there was a slide on this. Yeah, okay. You can see the iron ties. Yes, I forgot to mention. You can see the iron ties from this picture. All these small pink dots points are the position of these columns, which have been introduced for avoiding the out of plane overturning and provide a box behavior. Okay, so let's come back and let's go to the 2016 earthquake, the one that motivated this analysis. And in this case, the damage was mainly on the belfry tower. So you can see the type of damage very similar of the damage suffered in the 1997 earthquake. Also, the damage to the Camorcana walls and to the stuccos are very similar at that time. And there were also damage in some walls, but they are not documented because municipality immediately repaired them and replaster and repaint. So it's not possible to know how they were if they were widespread or not, and also the severity of these cracks. But since they repaired themselves, they should not be very serious damage. So let's go now to the next step, the description of the building components in the building. First of all, the vertical elements, the masonry. There are several different masonry in the buildings, and in order to facilitate the understanding, I classified all the masonry in 8 different types. So the first one is full bricks, and is the simplest one, I would say. And the remaining one is stone masonry. Stone masonry that goes from very irregular layout and bed degraded mortar to more and more regular layout, hewn stones, quasi-square stones, and then to this layout some brick courses are added. And then we go to the good, I would say, layout, again with stones that are quasi-square, and even on these there are brick layouts that are added in some cases. And the best quality is hewn stones with, in some case, thick bed joints, and in the best case, very thin bed joints. So there is a continuous variation in terms of arrangement, quality of stones, thickness of the bed joints, and so also the quality of the wall changes. And also for the bell tower, I had somehow to visualize these changes going from the base to the top. We start from good masonry with square stones and very thin bed joints, and then the bed joints increase. Square stones are still square stone, then the stones becomes quasi squared or hewn, then hewn squared, and so irregular layout, especially at this level, it's quite irregular. And then the bell tower, it's brick. So also for the bell tower, some dishomogeneity in the material. So in order to treat this in terms of following calculation, I listed all the walls in the buildings, and I found 20 walls, and each of these 20 walls has been considered as I would say, a percentage, a combination of the 8 types that I have identified, because there may be good mortar at the external part for the repointing, but not in the internal part. There could be one type of layer on the external part and maybe not the internal. So after all this examination, each wall, it's a composition of that 8 different types. And based on this composition, the properties of the walls in terms of strength and in terms of deformation can be evaluated. Most important information is that thickness is very high, up to 2.3 meters, but this in few cases, but generally 1.5, 1.8, it's normal in this building. The thickness reduced at upper stories, obviously. There is no what we call a sacco wall, so the quality of the masonry is more or less the same throughout the thickness, and also very important, as I mentioned, that the quality of the walls reduce going from bottom to top. This probably is due to the lack of financial resources during the construction. So let's see briefly the underground story. Look at the good quality of this wall, square stones, thin bed joints, brick walls, very nothing to say about this. And at the ground floor there are the brick walls at the entrance here in the first part of the building, while in the second part, in the back part, there is this wooden floor, but this is almost fake, I would say, because the actual floor is the prefabricated joist, prefabricated joisted floor with ring beams that I mentioned before, that is implemented only in this part. And on top of the walls here there are the steel beams, which are not visible, which has been implemented all over the hears. Even in this part, the quality of the mortar, that where you can see it, it's quite good. Going up at the first floor. The first floor is entirely reinforced concrete floor, and also the stairs has these ring beams in concrete with the steel floor. Remember the intervention that we have done. And here you have some picture of the inside. Most of them are plaster, so we had to in the campaign then to remove that plaster to check what was there. And also the second floor is entirely reinforced concrete floor, apart from the block of the previous stairs block, which is steel floor with reinforced concrete slab, obviously. Okay. These are the ties implemented in different periods. For the facade, they've been implemented in the 1500 transversal and longitudinal. Then there has been the ties implemented in the 80s in the roof, along the trusses. Remember, then there've been the ties implemented in 1994 when there was the refurbishment of the facade roof, so they are transversal. And then there are all the ties implemented during the 2001 works after the Umbria Marche 1997 earthquake, longitudinal, transversal, longitudinal, in all part of the building, basically. So many ties, hopefully. And here you can see from outside one can detect the presence of these many ties, and even from inside were visible, especially in the roof, under the roof, is possible to see all of them. The roof in general, but almost everywhere, it's not trussed, so there is no truss associated to the roof. Where the elements are inclined, there are iron ties that absorb the truss, so there is no truss, horizontal forces on the wall. In other part, for example, the roof of the coat of arm hall, even if it is inclined roof, but the beams are horizontal, so they are in the opposite direction than in the front, than in the facade, roof of the facade. So it's not trussing at all. And in the council hall, where there was a theater, we saw that there are trusses. Trusses with the lower element that absorb the horizontal forces, and also iron ties were added for this. So only maybe in the corner there could be some small trusses, because here there is the tower, the bell tower. So the solution for the roof has to be changed in this corner. There is an inclined rafter in this position, which is also supported by another small truss here. So maybe there could be some small truss in this part, but not even so much, I think. So basically the roof are not trussing roof. But there are other issues. For example, look at this. This is where there was a theater. This is the council hall. This is the council hall, and these are some. Here there are toilets, other places. So there is this wall that separated. This wall separated the council hall from the other rooms, and that wall is this one. So it's a hollow clay blocks, not very thick in depth, and which stop here without any top ring beams. and it's not connected to any I would say floor on top, any to the roof. It would be not so easy because here the roof is another maybe 4 meters, 5 meters because of the trusses. So it won't be easy, but nevertheless it's like a cantilever. It's a very large and long, I would say, very long cantilever, very high, because again also the height is quite significant. So it's really vulnerable. Going to the building survey and the in situ test, meaning this is the campaign that I have implemented in order to complement the information that comes from the existing documentation. So in order to design the survey campaign, one has to decide which is the knowledge level you would like to have, and according to this knowledge, it could be 1, 2 or 3, you have different partial safety factor of the resistance of the material. So if you don't want to penalize too much the materials and have reasonable results, at least you have to stay in the confidence level 2, which means 1.2, so 20% of reduction of the resistance of the material. Ideal would be to be on confidence level 3, which is confidence factor 1, meaning no reduction of resistance. What you get from experimental tests, you use somehow in the calculations, in the design, but the number of tests and the knowledge to reach this level is so high that it's practically impossible. For cultural heritage, the approach in our guidelines is a little bit different. There are 4 factors: the geometry, the building behavior, how it is understood, the mechanical properties of the material, soil foundation, and according to the different let's say level of knowledge of these factors, you came up with a partial safety factor to be added or that reduce the strength of the material. And in this case, for a reasonable let's say number of tests or knowledge of the structure, one came with the same number, 1.2, which means confidence level 2. So basically the two approaches for the ordinary building and for the cultural heritage, at least in this case, were similar. So based on this, I designed the campaign, the survey campaign, and this has been let's say influenced by some important factors. First of all, a lot of different masonry types. The Italian code requires to perform tests for every type of masonry, for every type of material, and then it's not just the different type in general, but also the quality. It's not just that it's different, but you realize that the quality is very different from the lower story to the upper story, so there is a need to investigate. And there are also a lot of other materials. It's not just masonry. There is reinforced concrete, so meaning concrete and steel, reinforcing bar. There is the steel of the floor steel. There is the steel of the iron ties, implemented in several periods, in the 1500, in the 2000. I mean, we cannot expect the same resistance, the same properties. So at the end, it's really dishomogeneous in terms of material use. This type of building. There are bricks. There are different type of wooden roof that were changed in the 90s, and there were older roof. It's really quite diversified in terms of material. So this is the reason why the campaign was so extensive, more than 100 in situ tests, several site inspections to understand geometry and detailings, and to support the company that was in charge for this test. Important also to know that these tests were committed by municipality independently from the assessment. So in this way there is some, I would say, not flexibility, but there is no interaction between the commitment of the assessment and commitment of the test. All the tests has been located on the plans in order to have a clear picture of where to perform these tests, or to have guidance for the company. But not only for this, also to understand if the places where these tests were, let's say, decided, really were able to get the significant information that you need for the analysis. So if you want to know some connection of vertical walls, you have to investigate some key points. So placing them on a map, you understand if they are distributed all over the floors, all over the corners, and not just in one of them. If you want to understand the anchoring of the floors to the wall, and you have different soil, different floor types, then you have to understand if you have taken considered in the analysis all of them. So it has been, due to this homogeneity that I told you, it has been quite complicated to investigate all possible different, let's say, conditions and materials. So the report also, it's quite consistent, quite heavy also to analyze, more than 300 pages, and contains all the results of all the tests. So let's go now briefly through the investigation that we have done. The first one is visual inspection, removing plaster at least 1 by 1 meter on several walls, and we have found very, or let's say, good layout, but also very irregular layout with very degraded mortar. In terms of mortar, we had made two types of tests. One is for the composition and one for the resistance penetrometric test. For the composition, it is clearly lime mortar. It's not cement mortar. Very weakly hydraulic, and the consistency is from loose to moderately tough. So basically, it has some friction behavior rather than cohesive behavior. And this is also demonstrated by the resistance. The average compressing test strength from the penetrometric test is 0.8 megapascal, which is not so high. But then I decided to perform some additional analysis. Always remember to take the results of the test and make some analysis on your own on this test. I separated the repointed joints from the not repointed joints according to the information that I had, and if the resistance is evaluated, its average over the only repointed joints, the resistance becomes 1.2, so increased, while decreased to 0.6 megapascal for the not repointed joints. So since the repointing of the joints, it's only in the initial, I would say 7 centimeters, maximum 10 centimeters from the surface, from the end of the wall, the surface of the wall. Then with such large walls, 1.5 meters, 2 meters, we may expect that the internal part, it's not the resistance of the mortar is in the order of 0.6, because it has not been repointed. Here you can see the bed joints and their layout of the walls, and the bed joints in the underground story and the ground story. So in this case they are repointed, they are very good. But this is the case of not repointed joints at the first story, and if you enlarge this picture, you can see that the mortar is really degraded. It's almost sank. And the same occurs at the attic. I mean, just below the roof, in the council hall room where the theater was, and just with your finger you can remove and make holes in the mortar. So this is clear evidence of the quality of this mortar. Endoscopies and endoscopies were requested in order to understand what's going on through the thickness of this wall. Sometimes these walls are made with two very good external layers, and then inside almost everything. I mean, bad quality mortar, bad quality stones, bad arrangement. But in this case we found from endoscopy, and also from the cores that we extracted, we made not so many cores, just 3 in the buildings, but many more endoscopies, which are less intrusive. We found out that basically the quality of the mortar is more or less the same across the thickness. So it's not made by 2 layers, the so-called Asacco mason. It's not made by two layers and other material, loose material inside, but it's more or less homogeneous. And this is also confirmed by the ultrasonic test. You mount the receiver on one side of the wall, you make the inputs on the other side, you measure the time lag of the arrival time of the inputs of the pulse, and then you based on the distance you measure the velocity of the waves, and in this case velocity of the waves was in the order of 1200 1400 meters per second. So this means that it's it's average low value, meaning that in any case there are no significant voids in the masonry. There are it's almost homogeneous masonry. It's not bad value, I would say. So again, it's a proof that in about the homogeneity of the body. Strength of the material. We perform a flat jack test on 4 different types of masonry, going from the well arranged and square masonry with thin bed joints to a little bit more irregular layout with brick cores, the full brick masonry, and totally chaotic and irregular masonry. And we found several different, obviously, resistance, and we compared this resistance. I compared this resistance with what's suggested by the code. So what we found, that in best quality masonry we get 6.3 resistance, which is a little bit lower than the range suggested by the code, considering several factors. I'll not go through this detail. Important is to understand the value with respect to the range. In this little bit more irregular layout, we found that the resistance is even more than what considered in the code, and this is probably due to the fact that these courses are very, the distance of this course is quite small. Usually there are 70-80 centimeter, even 1 meter distance. Here we are talking about maybe 20 centimeters, so it regularized very much the masonry. Full brick masonry, we obtain a value which is in the lower part of the range suggested by the code, and for totally irregular masonry we obtain a value which is even lower than the range in the code for a similar type of masonry. But we know that for irregular masonry the results of the flat jack test, it's not so high, because the flat jack could rest on part on stone, part on mortar, and according to what really happened at the support at the interface of the flat jack and the masonry, there could be very different behavior. So it's very uncertain, it's very scattered, the results. And what is worse is that for good masonry, the information provided by the code, it's quite reliable, and then it's quite high value. You don't need so much precision. You would like to have more information on the chaotic masonry, and in such case the experimental tests are not very much reliable. So this is really a problem. So somehow we don't have, as engineer, to be so strict with this number, even if I understand that authorities in charge of control usually are very strict, and they say if you got 0.5 you have to use 0.5. This is a very questionable, debatable issue, and I'm not fully agree with this if you make some interpretation, but nevertheless this is the value that has been used in the calculation as well. Anchoring of the vertical walls at the corners, there are several situations. In this case it's well anchored, in this case also it's well anchored, in this case it's anchored on one part and not in another, in another case it's totally not anchored, while for the floors and for the roofs, due to the presence of steel plate in the roofs, and due to the the joists are prolonged into the walls, and there are very often not reported in this picture, tie beams or ring beams or beams resting on the masonry walls, the floors can be really considered well anchored to the floors. Information on the floors or confirmation of what we had from design has been done through X-scan test. The X-scan instrument, it's a georadar with 3 antennae, which is able, due to these 3 antennae, to evaluate the properties along the thickness of the elements. So you have information on how is the reinforcement on the 2 direction in plan and on the thickness. So this gives you a 3D information from where you can get, for example, the thickness of the finishing, the thickness of the slab, or the spacing of the beams, and sometimes also the thickness of the joists, and so on. Compressive tests on concrete and tensile strength on reinforcing bar. They have been performed on 2 samples for what concerns the concrete and 2 samples for what concerns the steel, obtaining quite different results. 9 and 17 megapascal in terms of concrete resistance, compressive strengths, and 380 more or less and 450 more or less for the heel strength of the steels. And what is interesting, you see that the lower value, 9 megapascal compressive strength and 380 yield strength of the steel, are in the part of the floors which have been implemented in the first stage of first phase of the work, while in the second phase of the work the values are quite different. But first phase and second phase of this work has been implemented at a distance of few years. So even few years of distance, having different working company on the field may provide quite different results. And this again complicate the properties, mechanical properties evaluation. It's not just one concrete, it's not just one steel. So just to let you understand how complex may be really to characterize these buildings. And lintels, again, we found lintels made by full bricks, lintels made by wooden beams, 5 wooden beams, and lintels made by, in this case, 3 prefabricated, probably pre-stressed reinforced concrete joists. So again, very difficult identify in any place where is that type of lintels. And for the iron ties, similarly, we have iron ties implemented in different periods. So and even with different shapes and diameters, round, here they are square, and we try also to evaluate the geometry of the anchoring plates. For some of them we have, because for the ones implemented in the after the 1997 earthquake, there are drawings, so everything it's there. But obviously for the ones in the 1500 we don't have information. We had to make some survey on this. The roof trusses, wooden roof trusses, geometry has been evaluated for these elements, and the steel plates and also the thickness of this element has been evaluated. Let's go into the soil type now. Soil, the palace is located on a crest, where the slope in one direction, in this direction, is much more than the slope in the other direction. And there were already some information on the soil condition due to other studies. In particular, there was one geotechnical survey, one mass test that produced the shear wave velocity profile, and one H over V test, which provides some information of the main frequency of the field, so resonance of the soil. And on top of this, we put 3 new trenches to understand the location of the foundation, the depth of the foundation, and 3 new HV tests in order to complement the existing one on other side of the buildings. So these are the results in terms of trench located on 3 different sides of the building. Generally, the model, the geotechnical model, is something like that. The geological bedrock, which is not the seismic bedrock, but it's the more the soil with adequate strength for the for foundations. It's a blue clay or sandstone, so it's quite resistant. And then there is a colluvial soil, clayey loam, which is less resistance and more deformable layer. This geological bedrock has been found in different positions in the 3 survey, and basically just below the tower, this bedrock, geological bedrock, is at 40 centimeters from the ground, and the foundation is 40 centimeters from the ground. So basically, the tower is founded on this firm soil. If we go on the stair block that was added in 1500, then we find that the geological bedrock is 1.7 meter, while the foundation goes deeper in it, 2.1 meters. So it's something like this. So again, we are in a good situation. But in this part, we found, or the geologists found, that the bedrock is the geological bedrock, so the good soil, it's 1.8 meter, and the foundation are only 70 centimeters. So basically, we are in a situation like this. So at this corner, the building is founded on a more compressible soil, and this could be one of the reasons why in the past they decided to strengthen the corner column with micropiles. Maybe there were some cracks on the facade, but it is just an hypothesis. In terms of shear wave velocity, so seismic characteristic of the soil, the data are not 100% clear, in the sense that the mass that has been performed here, it clearly indicates a contrast of impedance at 12 meter depth, which is not the same depth where we have found the geological bedrock. So geological bedrock and seismic bedrock are different. The shear wave velocity below this 12 meter is in the order of 700 meter, and above is in the order of 300 meters, something like that. So very simple calculation tells you that we may expect for the upper layer some resonance in the order of 7 Hertz. 7 Hertz are more or less like here, and we can see that there is not any clear peak in this point. This is the H over V plot, which gave you the ratio of H waves over V waves, so horizontal over vertical waves in case of microtremors recorded in the ground, and they are plotted in relationship to the frequency. So where there are peaks, one may expect resonance of the soil, so side effects. So at 7.3 Hz, we don't see any significant side effects. Basically, we don't see significant side effects in all of these measurements, except this, which is in the order of 2.6, which is not even comparable with the possible resonance at larger or larger frequency. I mean, for having this frequency, you may have a deeper bedrock or more deformable soil, or you can have an additional contrast of impedance at depth. For example, if we consider at 160 meters of depth, which is quite high, a contrast of impedance such that it is much more stiffer than the 700 that we have until almost surface, then one may expect almost one hertz of peak, 1 hertz of frequency for resonance, and 1 hertz it's almost here, where there is a small peak, but really I don't know if it is significant or not. If it is considered significant, then it means that there are some effects really at a very large, huge depth. But honestly, all this data provide some information. I mean, the soil is quite stiff. There are no significant side effects. This is what I get mainly from this type of information. With this, we conclude the first part of the presentation, which has been devoted to the knowledge phase. In the second part, we will see the analysis and the results, the model and the analysis, the results, the intervention, and the conclusion of the studies. Thank you very much for your attention.